Oh, welcome back and thank you for joining. We'll continue with example number 3 on the lesson about applications of derivatives of trig functions. Let's read the problem first. A thin, rigid pole needs to be carried horizontally around a corner joining two corridors, which are 1 meter and 0.8 meter wide. So we have to find the length of the longest pole that can be carried around this corner. Now let's try to picture the situation first. So what we have in here is two corridors that are connected at a corner. And what we are trying to do is carry a pole around the corner. Now the pole is rigid, which means you cannot bend it so that you can carry around the corner more easily. Another condition given here is that the pole needs to be carried horizontally, which means you cannot hold it vertically. If you hold it vertically, you can carry a pole around the corner very easily as long as you have very high walls. So try to imagine that. So remember that if you want to carry a pole, right, in these corridors, so if you walk horizontally here, I mean, if you walk straight in here, then you can carry a pole as long as the length of the corridor, and the same thing is in here. Now, the problem will be how to carry the pole from one corridor to the other, so how to make it to the corner. So the maximum length pole that we can actually carry around the corner will be conditioned by the minimum distance between these two walls. So we are going to say that to find the maximum length wall, that means we have to find the minimum distance between the two walls. And we draw that minimum distance by making sure that we are not actually breaking the corner in here, because you cannot carry the pole this way, because that means then you have to break the wall, the interior wall, inside wall here, to carry the pole. So it has to go around this point. So you can touch this point, but you cannot go further than this. So I'm going to draw the pole here. I hope this made sense. The explanation made sense. So yes, the problem is asking for the maximum length pole, but what we have to find to determine the maximum length pole is the minimum distance between the walls in here at the corner, because the length of the pole would be conditioned by that. We cannot carry a pole that is longer than the minimum distance between the walls. So we are going to let the length of this pole be represented by letter L. And we are modifying this diagram a little bit now. Try to picture how, or realize here that the pole must be placed at a certain angle with this corner in order to maximize the length of it, or the room for making it around the corner. So we are going to let this angle that the pole makes with this wall be angle theta. Okay, you could have made this angle theta, it doesn't really matter. So we're letting this be angle theta, and we're dropping a perpendicular from here to here. So that will make a 90-degree angle. And with this, we have created a right angle triangle with one angle theta and one side of 1 meter in length. Now, in a similar way, we are drawing another triangle. So I'm going to draw the triangle by dropping a perpendicular to the inside wall. So now I know this is 0.8 meters. And we have a right angle triangle here. And now I have to look into the angles. Now, as you can see here, the angle theta is located, or is nested, in between the pole and this inside corridor. So this and this, so these two lengths will be parallel. These two sides will be parallel to each other. Okay, we should never say lengths, actually. We should say sides. So the two sides will be parallel to each other, because lengths are numbers, right? So they cannot be parallel. So these two will be parallel to each other. And the pole will act as a transversal that is crossing the two parallel lines. So this angle theta here then, and this little angle here, will act as corresponding angles, and they are equal to each other. So in other words, this is like the F pattern that we have done way back in elementary school or grade 9. So here goes angle theta. So now we know a lot more about each triangle here. So we know one of their angles and we know one of their sides. So we are trying to find the minimum value of L, which will make the maximum value of the pole that we can carry around the corner. So we're going to break down the length L from here to here into L1 and L2. So here is L1 and here is L2. So we say that the length L equals L1 plus L2. Now to find L1, we're looking into this right angle triangle. L1 is the hypotenuse of it. This side here is located opposite to angle theta. And we know that the opposite and hypotenuse are related to each other by the ratio of sine. So we'll say that the angles theta will have the sine ratio equal to opposite, which is 1 meter, over hypotenuse, which is L1. So that will allow us to express L1 in terms of sine theta. So 1 divided by sine theta. Similarly, we are going to find an expression for L2 using the other right angle triangle. So this time, this is the angle theta, 0.8 meters, which is the side we need to use because we know the length of it, is adjacent to angle theta. L2 is hypotenuse. So adjacent and hypotenuse are related to each other by the ratio of cosine. So we'll say that the cosine of theta equals 0.8 divided by L2. So therefore, we'll say L2 is 0.8 divided by cosine theta. So now we are allowed to find an expression for L. So we'll say that L is equal to 1 over sine theta plus 0.8 over cosine theta. So as you can see, we have expressed L in terms of angle theta. So we're going to write the equation in proper form. So L theta equals, and because we know we have to somehow differentiate this function, so we are going to rewrite this slightly differently. So since we have constants in the numerator, it will be easier to differentiate by converting these fractions into exponents or exponential numbers or exponential terms with power -1, and then plus 0.8, and then cos theta to the power of -1. So now we're ready to differentiate L. So we're going to say L prime theta equals. So notice that here we have an outside function, so the power function. So that will give -1 sine of theta to the power of -1 minus 1, so that's -2, and then multiplied by the derivative of the inside function. So the derivative of the inside function, so derivative of sine is cosine, so we'll write cos theta here. Now, in a similar way, we'll deal with the next term, so 0.8. So we have the outside function, which is the power of -1. So that means we have -1 cos theta to the power of -1 minus 1, so that's -2, multiplied by the derivative of the inside function, which is the derivative of cosine, and we know derivative of cos is negative sine, close the brackets. So continue simplifying L prime. So we have -1 multiplied by cos theta, and we'll bring the power of -2, the -2 term, power -2 term, in the denominator. So we have negative cos theta over sine square theta. And then in a similar way here, we're combining some terms, so minus and a minus will make a plus. So 0.8 times +1 times sine theta, they will stay on top. So 0.8 sine theta divided by cosine square theta. So this is the derivative. We have simplified somehow, but remember that we need to make this equal to 0. And for this, we will need the derivative to be expressed as a single rational expression because it makes it easier to find the zeros of it. So we have some more work to do. So that means that we will need to make the denominators the same. So we have the denominator sine squared and cos squared. So that means we're multiplying this by cosine squared theta over cosine squared theta, and we're multiplying here by sine squared theta over sine squared theta. So now you see that we have two rational terms with the same denominator, sine squared, cos squared. So we're going to draw a big fraction. We have sine squared theta, cos squared theta. And the numerator will have, let's take a look, negative cos times cos squared, negative cosine cubed theta. And here we have sine squared times sine. So sine times sine squared is sine cubed theta. And now we're ready to make this equal to 0, which means that we're practically making the numerator equal to 0. So let's write that down. We have negative cosine cubed theta plus 0.8 sine cubed theta equals 0. So as you can see here, we're trying to solve a trigonometric equation, and we have two different trig ratios. We prefer to have a single trig ratio. And when we have sine and cosine only as terms in a trig equation, we try to split them apart. So we're going to keep the 0.8 sine cubed theta on the left side. We'll take cosine cubed theta to the other side. And now we'll divide both sides by cosine cubed theta. And that is because we want to bring in the tan theta. We know sine and cosine are connected to each other by the ratio of tan. So the left side now will become 0.8 tan cubed theta equals 1. So that will make tan cubed theta equal to 1 divided by 0.8, or should we say 10 over 8, and even better, 5 over 4? So if tan cubed theta is 5 over 4, that will make tan theta equal to 5 over 4 to the power of 1/3. Now remember, this is an odd index, right? So, or an odd denominator, so we don't have to take plus and minus. Only with even denominators we do. So let's solve the equation now. Angle theta equals inverse tan. And then here we have 5 over 4 to the power of 1/3. Now use the calculator. Set the calculator to either degrees or radians. So I set mine to radians, and I got the angle theta 0.82 radians. So what that means is that, or approximately, if you want to convert it to degrees, is 47 degrees. So what that means is that we need to position the pole at an angle of about 47 degrees in here in order to maximize the possible length that we can carry around the corner. Now, if you want to check and see if L will have a min or a maximum at theta equal 0.82 radians, we use the second derivative test. Second derivative test. Beautiful writing. Derivative test, sorry about that. Okay, here we go. So second derivative test, we'll start off here with the first derivative. Now, the first derivative, let's find where the simplest form was. So the first derivative was, was quite good in here actually. So we can differentiate this, or we can differentiate this more simplified form, but this seems a little bit complicated. So it would be easier to differentiate L prime from here. So we have L prime theta equal to, so as you can see in here, we multiplied by sine squared over sine squared and cos squared over cos squared to combine them, but the derivative was negative cosine over sine squared. And the other term is plus 0.8 sine theta over cosine squared. So we'll differentiate this just for the fun of it. I'm going to bring this a little bit further down so we have more room to show our work more clearly. All right, here we are. Okay, so we're finding L second theta. So L second theta would be equal to, we're going to group, or we're going to differentiate each term separately because we have the sum of two terms. So it would be easier that way. So the derivative of negative cosine would be equal to negative sine multiplied by sine squared theta, and then minus the derivative of sine squared would be 2 sine theta times cosine theta. Remember, you have an outside function here and then an inside function. All right. So the outside function brought us to 2 sine theta to the power 1, and the inside function is the cos theta. All right, and then we multiply by negative cos theta, so by the numerator here. So negative cos theta. Now all of this would be over sine 4 theta. So we'll continue with the next term. So we have plus derivative of 0.8 sine theta is 0.8 cos theta multiplied by the denominator, which is cosine squared theta. And then minus the derivative of the denominator. So we have a little chain in here. So we have the power of 2, and then we have the cosine theta. So that means we'll have 2 cosine theta to the power of 1, and then times the derivative of cos, which is negative sine theta. And remember, this will be just the derivative of the denominator. You have to multiply by the numerator, which is 0.8 sine theta. All this will be over cosine 4 theta. So it looks a bit complicated. We'll be done in the next step. It's going to turn out quite easy and interestingly easy. So minus plus sine cubed. So that will make a positive sine cubed theta. Let's see what we have here. Minus plus, so 2 sine cos squared theta. This will all be over sine 4 theta. And then plus. So here we go again, 0.8 cos to the power of 2, so 0.8 cos power 3 theta. Minus, so 2 times 0.8, we have plus 1.6 sine squared theta cosine theta over cos 4 theta. So let's take a look at all these terms. Remember that theta is an acute angle. So since theta is an acute angle, the sine and cosine of an acute angle are positive. So here we have a positive number to the power of 3 plus double a positive multiplied by another positive divided by a positive. This entire fraction will have a positive value. So let's take a look at the next fraction. So 0.8 positive, a positive number to the power of 3, entire thing positive here, plus a positive divided by a positive. So it seems that we have a positive plus a positive. So without even having to substitute angle theta by 0.82 radians, which is an acute angle, just by a simple estimation, we can tell that L secant theta will be positive in value. Therefore, the function will be concave up. Therefore, we're going to say at theta equals 0.82 radians, the length will be a minimum. Now remember, this is the minimum length of the segment that connects the two sides of the wall, or the two walls. So that means that the maximum length that we can carry around the corner here would be equal to the length that connects these two walls when this is made, or the angle here would be equal to 0.82 radians. So we have confirmed that at theta equals 0.82 radians, the length will be a minimum. Let's find the minimum length. Now remember that the length is 1 over sine theta plus 0.8 over cos theta. So that means 1 over sine of 0.82 radians plus 0.8 over cosine of 0.82 radians. So let's check and see. Let me grab a calculator. We have 1 divided by 0.82. Make sure your calculator is set to radian mode if you're using radians, or degree mode if you're using degrees. So 1 divided by sine of 0.82, add 0.8 divided by the cosine of 0.82. Let's see what we get. 2.54. So 2.54 meters will be the minimum length that connects the two walls. So that connects the two corner walls. So therefore, we're going to say that the maximum length of the pole would be equal to 2.54 meters. So we cannot go higher than that because the distance between the walls won't allow for it. And I hope this made sense. And thank you for learning with me. Bye for now.